Hi, and welcome to today's Rust Linz meetup. We are so glad to have you here on this wonderful evening. I don't know where you are, but here in Linz in Austria, the weather is beautiful. The sun is shining. We have blue sky, the best possible conditions for having a great evening with two Rust talks. As just like as always, we start our evening with a round of community news. I will share my screen for that and run you through a few slides that I have prepared. And after that, we will dive right into the first topic with a great guest speaker that we have today for you. So let me share my screen, and here we are. Yeah, this is the 23rd Rust Linz meetup that we have. And yes, you are right. We do monthly meetups. So next month, we have our 2-year anniversary. Ooh, we are so much looking forward to that. We are currently planning what we can do. We already have a great guest speaker on our schedule, and we will try to do our very best to have a great program in this second anniversary meetup. We are looking forward to it, and we hope that you all will join us there. Now, if you are a regular viewer of the Rust Linz meetup, you know Rust Linz is part of the family of the coding club Linz in Austria. We are a volunteer-driven coding club which does a lot of different activities, and Rust is very near to our heart. Now, today's speaker, we want to welcome Zelda as our first guest speaker. Zelda is a Rust enthusiast and member of the AWS Rust SDK team. Thank you, Zelda, at that point already for being with us. We will say welcome to her in a few minutes. She will kick up the evening with her talk, and then I will do a short beginner-friendly talk about consts and constant function evaluation in Rust. I hope this will also be interesting for everybody. If you would like to get in touch with us, you can do that via our Discord server. Here you see the link. You can also go to rust-linz.at, our website, and there you find not only just the recordings of all previous talks that we had at Rust Linz, but you can also find links to our Twitter account, to our meetup page, and of course, to our Discord server. You're very much invited there. You can ask us questions. You can get in contact with me or Stefan if you would like to, for instance, propose a talk or something like this. Discord is a great way of keeping in contact. Now let's start with the community news. Our very first announcement is, that's a tradition, our Coder Dojo Linz announcement. Coder Dojo is a programming club for kids. We are Austria's largest and most active programming club for kids here in Linz. And the next meeting is, as every week, tomorrow on Friday. Every Friday afternoon, we invite kids between 7 and 17 to do some coding with us. The Coding Club Linz, the workshops for kids is in German. So independent of where you are, you're always invited. If you have kids or nieces or nephews or whoever you know in this age group between 7 and 17, this is completely free. It is completely open. All the kids need to be able to speak a little bit of German, and they are very much invited and very much welcome here at the Coder Dojo Linz. Female coders, our friends at this meetup, the Female Coders meetup. Female Coders is a group of passionate programmers, female programmers, who invite regularly to coding groups, to working groups, where women and girls can either start with coding or build a network of female coders. This is what they do. Female coders have currently summer break, but they already announced a great thing. 2 times a year, they traditionally do their large hackathon for women and girls. We cooperate with them in the Coding Club Linz, and this hackathon, save the date, will be on the 7th of September. So if you live near Linz or generally in Austria and you would like to participate there, you're very much welcomed. Now, Stefan is today not here with me. Stefan, the co-organizer and co-founder of Rust Linz, he has to care for his kids today, so he asked me to do the moderation today. But he is not just organizing the Rust Linz meetup, he's also organizing some other meetups, and one of them is the Technologieplauschall, which is a very popular meetup here in Linz. And the next meeting at the Technologieplauschall will be at the 24th of August. And take a look take a look at the topics here. There is a very important and interesting topic that I am very much looking forward to. WebAssembly is already on the agenda for the next Technologieplauschall, 24th of August here in Linz. Now, the second meetup, which Stefan is organizing regularly, is the Stahlstadt meetup. It's about the JavaScript and TypeScript community. And in this case, the next meetup will be on the 12th of July. So if you are very deep into web development, maybe you are a full stack developer using Rust at the back end and JavaScript and TypeScript in the front end, something like this, then definitely check that out, stahlstadtjs.org. This will be a great meetup. There was a pretty long break for Stahlstadt meetups because of COVID, but now they are back and they do great meetups, and I'm pretty sure that this will be an exciting evening. Many people have read it. There will be a Eurorust conference. It will be a 2-day conference in Berlin and online. This is part of the Eurofest family of events. I wanted to point that out. They have currently opened their call for papers and participation. So if you want to take a look at this conference, I'm pretty sure this will be awesome 2 days. And if you are a speaker, or if you want to get into speaking, and if you have something interesting to share, I'm pretty sure that the organizers would like to hear from you. You can use their open call for participation. It's online now. At the end of the community news, we want to say thank you to our sponsor, Microsoft. Microsoft is offering a great learning platforms and technical documentations. And if you want to learn more, for example, how to create a function with Rust and Visual Studio Code, please either take a screenshot here, type in the link, scan the QR code, and I will also share the link in a second in the chat, so you can also just click on the link in the chat and take a look how it works to write functions in Rust and Visual Studio Code. Thank you very much for our sponsor, Microsoft, for supporting the Rust Linz meetup. And that was our round of community news. Let's take a look at the watch. Yeah, it's perfect. We nearly took 10 minutes. I think Zelda is already here, and I will get her up on the stage. Give me a second. Hi, Zelda.
Hey, everyone. How's it
Hi.
going?
Hey, we are so glad to have you here.
I'm really excited to be, virtually here. It'd be kind of cool to
Virtually.
actually be in Linz, but I'm in Chicago right now. So
Chicago, that is typically a question that I ask our guest speakers regularly. Where do you broadcast from? Chicago? Okay, interesting. Do you have a vibrant Rust community in Chicago?
we did. I used to run the Rust meetup here, and I've
Oh,
actually been
really? You do?
slacking on that. So if we don't, it's definitely my fault. But yeah, we actually do have a lot of Rust stations here in Chicago.
Very interesting. Super. Zelda, let me say thank you very much for taking the time. We know that we all are pretty busy today. Whoever is in software development, and especially now with some things going on in the world, it's not easy to take the time. And we really value that you take the time to tell us a little bit about Rust at AWS, Rust in your environment, in your job. And we are very much looking forward to your talk. I will try to bring your slides up to the screen. Let's see if that works. I think that looks pretty good, right?
Mm-hmm. Yeah,
Okay.
that looks right.
So are you ready?
I am absolutely ready. I'm very excited.
Very good. We are looking forward to your talk. Zelda, the stage is yours. Thank you for being with us. And please tell us a little bit about how AWS is building the Rust SDK.
All right. Yes, it is my pleasure to be here. I'm very excited to present on this. I joined the AWS Rust SDK team several months ago, almost half a year now, and I've been helping them build it. And I've also been presenting on it a little bit. I presented at reInvent last December. For anyone that's not familiar, AWS stands for Amazon Web Services. So what am I going to cover tonight? We're going to look a little bit at how to use the SDK to send a request to S3, which is our simple storage service. We're going to look at what actually happens with that request as it's getting sent. We're going to talk about how we actually code generate all these SDKs for 300 plus services. It was 316 different SDKs that we produced the last time we counted. And we're also going to talk a little bit about what you can do if you're interested in contributing to the SDK, because it's all open source. And then, of course, at the end, we're going to have time for questions and answers. So to start, making a request to S3. Now, there's a lot of extra context for people here. I've shared these slides in this Meetup's Discord channel so that people can click on all these links, because every few slides, there's going to be 4 or 5 links for you to take a look at. I've linked here are 2 repos, one for the SDK and one for the code generation repo. I've also linked our repo that contains all of our official examples. I've linked the developer guide that we put up a little while back. I've also linked our crate documentation, so you can just jump right in if that's what you're interested in. Now, we only have a limited amount of time, right? So there are a couple things I'm not going to be covering in this talk, and that's going to be stuff like creating an AWS account, how to get and store your access keys, how to create a new Rust app with Cargo, or I'm not going to talk about how to do async runtime stuff with Tokio specifically. We're going to be using it, but I'm going to kind of gloss over a lot of the basic things. However, again, I have included links to all those things. So if you're not familiar with any part of that, you can go click the link and get some more information. So first things first, we want to make an app that interacts with AWS. Now, whenever we're doing stuff with the SDK, it's pretty much all happening async. We use Tokio a lot, although technically the SDK can be runtime agnostic, which I'll talk a little bit about later. But in this example that we're looking at, we are defining our main function. We're saying that it's fallible, that it might return an error. We're initializing logging, which is always a really good thing to do. We have a lot of logging set up in the SDK to help you understand what's actually happening. And the first real thing that we're doing here is on line 5, we're creating a config, an SDK config. Now, an SDK config is responsible for collecting all this information from your system and making it available to the clients that we're going to use to make requests later. Every client kind of has its own needs, but there are a lot of shared things that they need to know about, and all that is encompassed in this struct. And all we have to do to create one is call AWS config : load from env, and then await that, and that's it. This will read your environment, your file system. It might even make calls to like fetch credentials from remote sources. And it does this by looking at things that are the same for every single AWS SDK. So if you've already set up your computer to work with another SDK for AWS, like the Python SDK or something like that, then this is kind of like a drop-in replacement. You can just run this and it's going to load all that configuration from your environment. So next, we're going to create our client. Specifically, we're going to create a client to talk to our simple storage service. Now, I may have mentioned earlier, simple storage service is for storing objects, basically just any data. And it organizes that data into buckets, and you refer to that data with keys. So here, we're creating our S3 client. And all we have to do that is to pass it that shared config. And then that's it. We now have a client. Next, we're going to use that client to create a builder function for our request. All requests in the SDK get constructed by these builders, where you say what builder you want, you call methods to set any inputs that it might require, then you call send, and that's going to turn it into a future, which you can then await. And then because this is Rust and because these requests might fail, you'll see that we have that little question mark try operator at the end, which if an error occurs, it'll bubble it up and then get emitted. And that's it. Like you can create your config, create a client, make a call in just 3 lines like that. For most users, it's going to be this simple, and we're really proud of how easy we made that. Of course, it's not really that simple, right? Like a lot is actually going on. So what's really happening under the hood when we do all that? Well, first, looking at that config, what we call load from env, what that's actually doing is it's calling this function called from env under the hood. And from env makes this thing called a config loader. And the config loader is responsible for doing all those things I talked about, looking at your environment, looking at your file system, and so on. And then it just calls load on it. And that means you get all the default behaviors from it that you would normally do. We're not overriding anything or replacing anything from the environment. And then we just immediately await it so we can get our config back. So you can manually create these config loader structs, but really you shouldn't need to. It's best if you use load from env and just rely on storing all your config in your environment as opposed to setting things manually in your program. However, if you do need to do that for testing or because you think it's going to provide a better experience for users of your app, then that is okay. So the config loader sets all these different things. It collects information like what your app's name is, which we use when logging things and making requests. Your credentials provider, basically like, are your credentials for AWS coming from your local environment? Are they getting loaded in one of the standard ways that we have for doing that? That sort of thing. We also have an endpoint resolver. That helps us know where to send these requests because AWS is really big, right? And so this will figure out exactly what URLs to send each of our specific requests to. And again, you can override that if you need to test. And you can actually point it to local stack, which is sort of like a local testing version of AWS. You also have to provide a region because AWS is regionalized. When you set up something like S3, you put things in specific global regions. And that's basically an abstraction over the location of these things. Stuff that's closer together will run faster than things that are farther apart because that's the internet. You can also set retry and timeout related stuff here. And that's just, basic things for making an HTTP request. An interesting one in between those two is sleep. And so earlier, I mentioned that we're kind of agnostic over async runtimes. So this is how we can achieve that. At the very lowest level, what we really need from an async runtime is the ability to thread sleep, the ability to say, wait for this amount of time, and then tell us when that time has elapsed. We need that for retries. If a SDK is getting throttled because you're sending a lot of requests, we have to be able to wait. We have to be able to see when a timeout has elapsed. And so by allowing people to supply their own thread sleep function based on whatever executor they're running their program on, then this will allow everything to still just work. We also have a provider config. That is our abstraction over things like your environment variables, your file system, things like that. And that's really helpful during testing because in testing, you want to be able to run tests in parallel probably. You don't want them to all be setting stuff in the actual environment and overriding things. You want to be able to set a specific, consistent, environment for each test. And so we do that with the provider config. And then lastly, we also want the SDK to be generic across HTTP frameworks. Right now, it's pretty heavily based on Hyper, but we're slowly adding the ability to switch out different parts to use whatever HTTP framework you think is best for your needs. Okay, so that's a lot of information. Like, where does that even come from? Well, it gets set mainly in two ways. These kind of very simple config structs where it's just saying like, hey, for this, just insert this small piece of config into the larger shared config. It's just structs filled with data. Determining default values in this case is really simple because they're either just hard-coded things or they're just left unset. But for really complex things, like credentials and so on, we use these things called providers. And provider is some sort of trait object that optionally returns one of those config structs. And we box or arc them so we can pass them around, but not worry about ownership. So one of the cool things about providers is that we're able to chain multiple providers together. And so one example of doing that is like, say we want to get your timeout config. You could define that with environment variables. You could define that in your AWS config file. And we have to look in all those places to understand how to do timeouts that you want, right? And so what we do is we make a separate provider for each one of those situations. And then we chain them together into this kind of super provider. And that's what we use to figure out how to set your settings. These are great for when determining default values is very complex, because we have to look in multiple places, or because we might have to make async calls. We might have to call some sort of service that will provide the credentials on the spot. And that's basically how all that stuff works. So I said earlier that you generally don't need to override these things, and it's best to set them in your environment. However, we do, of course, provide the ability to do so. So in this example, we're doing from env instead of load from env. And that allows us to modify this config loader before we actually use it to get all that config from all those different places. And in this specific example, we're saying use the default region provider, and it's a chain, so it's going to look in multiple places to figure out what region you want to send requests in. And then we're saying if they haven't set anything for that in any of those places, we're going to fall back to the US East 1 region. One thing to be careful of, and a mistake that we see sometimes, is that when you're overriding these things, you have to make sure that if your provider that you're inserting here might not provide something, then you should probably combine that with the default provider, right? Because if you get rid of the default provider, then there's a chance that you're not going to set anything here, in which case the SDK is going to panic, so that we can bring your attention to this as early as possible, because we can't send requests without these things generally. Okay, so further under the hood, all services that make up AWS, they all have their own config struct that implements the ability to convert from a reference to that shared config to a services specific config. So why do services need their own config? Most of them are exactly the same as the SDK config. However, a couple services do have these service-specific options that they need. And by creating service-specific configs, even for services that don't need them, it allows us to preserve backwards compatibility if they need to add those service-specific things at a later point. One example of a specific thing is that our Elastic Cloud Compute service, EC2, requires an idempotency token to be sent with a lot of different requests. So when creating a service client, the client new method takes that reference to an SDK config. It's calling that from impl under the hood to convert it to a service config, and then storing that within itself. And for testing purposes, it's totally possible to create a client directly from a service config and an HTTP connection. And we're going to kind of look at that a little bit later. And there are two main things to focus on. There's a lot of text in this area, but what's really happening is that we're setting up some kind of middleware, and we're setting up some kind of Smithy client. What is middleware and what is a Smithy client? We'll talk about that in a second. But what this code is doing is it's taking a service config that we got because it automatically got converted from us or for us. We're looking at the retries, the timeouts, the sleep implementation, things like that. We're setting up this thing called the default middleware, and we're putting that all together in this builder that eventually produces a service client for us. And that service client, you can see it has that arc and there's a handle inside it. We're also going to talk a little bit more about that in a second, what's actually happening there. So before we get too far ahead, what is a middleware, right? Not everyone is a web programmer, so they might be unfamiliar with this term. Middleware is basically a way of defining reusable behavior for either your client or your server. And sometimes it's general purpose behavior, sometimes it's more application specific. So a general purpose thing might be like logging or something like that. And a more specific thing might be some form of request signing. So you would set up a bunch of middlewares, one on top of the other, and then it's like a pipeline that you can send a request through or that you can send a response through, and it will inspect it and modify it as needed. So at the end, you have a request that's ready to be sent off to some service, or you have a response that's been processed in whatever way your app requires. And then Smithy is the name of the language that all of the AWS services are modeled with. Smithy RS is our specific code gen tool, or rather collection of a bunch of tools. But Smithy itself is kind of the whole thing. It's the modeling language itself. Okay. So all services right now use the same middleware stack. We have basically like a couple of default things that we're always going to need when we're making requests to Amazon stuff. So that includes like that endpoint resolution, which we talked a little bit about in the config thing. Like config will set all the logic for how that happens, and then this will set up the thing that will actually figure out where stuff is going at the time we send the request. It'll allow us to insert user agent headers into requests. It will allow us to sign requests and basically set these authorization headers, which are sort of like credentials. Technically, they're not, because sending your actual credentials in a request would be unsafe. And that default middleware, it's just what I said. We're setting up these layers. And so these different layers, we've defined these specific ones, but they're very generic, and they're based off of this lower level framework called Tower. And Tower is just this general framework for defining services for HTTP stuff. And the service can like literally be like you sending requests to something, or something sending requests to you. The abstraction fits on both sides of the sender and receiver kind of thing. In our case, we're just sending and then we receive. But yeah. So I mentioned a Smithy client a little while back. I've also talked about service clients. Those are different things, and it can be kind of easy to get them confused when you're very new to the SDK. I know it was a little hard for me at first. Service clients are actually a wrapper around that service's config that it needs, and then like a pool of actual HTTP clients, the Smithy clients as we call them in this. And a Smithy client is a Tower service composed of a bunch of different layers. Again, just like the middleware. It's actually almost the same thing. It kind of looks like the same thing, except it has a couple of extra things like timeouts, retries, how requests get dispatched, deserialization, things like that. We're going to look at that in a little bit. The takeaway is that Smithy clients consume operations in order to send an HTTP request. So, under the hood, dispatching an operation. So this is like earlier when we had that list buckets thing and then we did send. Under the hood, we're dispatching an operation. So requests made to a service are represented as operations. In the model, like this actual Smithy model, the word operation is a shape, a kind of thing that associates inputs and outputs and request-specific errors. And in the SDKs, we have a type called operation, and that gets created from an input sent by a client, and then either the output struct or an error struct is returned in a result. And the function that we use to turn that input into an operation is, unsurprisingly, make operation. And it does that actual conversion. It makes the operation, which inside it contains an actual HTTP request, which is like a specific Rust library, the HTTP library that pretty much all web frameworks in Rust are based on. Yeah. So operation construction. When we're creating that service client, that's like setting up the config, setting up the middlewares like we talked about. The next thing that we do is we call an appropriate method to create a builder. So in our first example, that was list buckets, and that starts building a list buckets input, which is going to be used to create that list buckets operation. And importantly, that builder inside it has a handle to the Smithy client. So our service client created this thing that has all the information needed to send a request, and it copied or gave a reference to its internal HTTP client, so that request can just be sent at its own leisure, or rather at your leisure. So next, we set all the required configuration for that builder and then call send. So in the list buckets example, we didn't actually have to set any different things, but we're going to see an example in a minute where we do set a couple of different fields. And it all happens through calling methods on a builder. Next, after send is called, the send method is responsible for building the input struct from all those different things that we just set, and it converts that into an operation with make operation. And that's where you'll get an error if we can't construct an HTTP request, which is, I struggle to think of a situation where this would actually happen. It'll pretty much never fail. But if there was something wrong with it, if something caused the request that was created to be invalid, this is where you'd see an error, and it would tell you what you should do about that. Then the send method will pass this new operation it's just created to a Smithy client's call method. Okay, and so I've produced a couple things here so we can see like what send looks like and what happens with like operation construction. So here we can see a send method for list buckets, and we can also see that it's calling build. That's where we're actually getting that input struct. It's mapping the error into a construction failure just in case there's an issue with that. Then we make an operation by passing it config that it needs to understand how to make an actual request. We wait for that to finish because sometimes creating an operation might require some async something like reading the file system or sending off a request. And then we also will map that error into a construction failure. And then at the end of that, we have our operation, and we pass that to that client that we have, the Smithy client, not the service client. Okay, low-level tangent. Like, we keep going deeper. I'm going to go a little extra deep for a second here. Okay, we can do a lot of this stuff manually. When we did it the nice way, it was 3 lines, right? And it just worked kind of magically. But for testing, we often do it the more difficult, specific way because it lets us override a lot more. So in this case, we're building a service SDK directly by getting the config builder, setting a credentials provider with like hard-coded testing credentials, setting the region to always be US East 1. We're creating our own HTTP connection and injecting that into a service client's new thing to create I misspoke. Here we're actually creating a Smithy client. So normally we create a service client that has multiple Smithy clients inside it, potentially. But here, we don't even need that. We're just going to create our Smithy client directly. Then we create our operation manually. So we have our input here that we're saying, this is for put object, by the way, not list bucket. So we're calling builder methods on it. We're saying, I want to put an object to my test bucket. I want to name it key.txt. I want to, it has this body of some test text. So that's what we're going to upload as the actual object. Then we call build. That takes that builder that we just constructed, turns it into an input. And that could fail, but since this is a test and we know it's not going to fail, we just unwrap. Then we call make operation on that resulting input, and we have to pass the service config into it, just like we saw was happening for us when we called send originally. And we have to await that, just like I talked about before. And then next, we do a cool thing that we do in testing, where we can actually take that operation before sending it and insert certain hard-coded things. So like we hard-code the date that the operation is getting sent, because we're going to check the request at the end of this test, and we don't want that check to fail because the request was sent later than the first time we did it, right? We want to hard code this stuff so that our tests are repeatable and consistent over time. And we also insert a specific user agent for testing. Then we call the call method ourselves. So everything that I've just covered, all of that happens automatically when you call send. But as you've seen here, if you have specific needs, normally testing, you can kind of do the harder, more verbose version and switch out any part of it that you need for whatever purpose you have. So when call happens, a lot of interesting stuff is happening in there too. We actually create a new tower service whenever you call. And it's basically its own server that has one job, just to send your request, and that's it, nothing else. It will modify that request by passing it through a bunch of different layers, and then it will actually dispatch it, send it over the wire. And then when it gets the response, it's going to deserialize that either into the successful struct or some error, right? And return a result to us. Now, errors can happen for all sorts of reasons, things like a connection issue, or maybe there's DNS issues or socket hangup, things like that. Or it could be the service responding with an error, like, hey, you're sending me too many requests, or you forgot to set this required field in your request, or the thing you were looking for told me to look for doesn't exist, stuff like that. And so inside that call method, this is what it looks like when it's constructing that service. It creates a new service builder. It adds timeout layer. It adds this layer for retries. It adds another timeout layer because we actually add one layer per kind of timeout we support. We support multiple kinds. It adds a layer that will parse the response into some actual Rust struct when it comes in, or an error, hopefully not. It inserts that middleware that we created earlier and stored in our services config. It creates this dispatch layer, which will take our operation request and actually dispatch that request over the wire. And then lastly, we define that connector, which if you're doing this automatically, like if you're doing the nice 3-line config client send version, that connector is going to be determined for you. It's going to be based off of Russell's Rust TLS, or like a native cert, some sort of HTTPS connector under the hood. And we basically pick that for you, although you could replace it if you wanted. And then in that testing example that we saw, this will be that test connector. We actually have a bunch of really cool test connectors for this. Like, we have one that will inspect every request you send with it to make sure that it looks the way you expect, and that will respond with these canned responses so that you can make sure that your app always handles the responses in the way that you want. Another cool thing, though, is that like when we create this stuff, because it's creating a new service stack, we don't have any confusion about like if we change the configuration, is that going to change what's going to happen with my service before I send it? Like, you don't worry about stuff like that, because this has all of that state contained within it, and it's perfectly ready to make that request at any time. And you can make a bunch of these services just on the fly, which really surprised me when I first started out. I thought it was like kind of weird, but it's actually really cool. And that's it. After only, I don't know, like 1,000 steps, right? We've actually sent a request. And it's great that like all that can be so easily expressed in just those 3 lines. So that was a lot of Rust code we looked at, right? Like, where does all that come from? It's got to come from somewhere. I said that there were 316 services. I'll tell you, we don't write it all by hand. We have to code generate it, right? So how do we do that? It's Kotlin. We use a bunch of Kotlin, actually. We had considered using Rust for this, but all the canonical tooling for Smithy, which is a pre-existing thing that all the other AWS SDKs are based on, all that tooling is written in Java. And so in order for us to like just get started right away writing this SDK and getting it out to people that need it, we decided that it was a better idea to take all these great things that already existed and build on top of them rather than try and replace them, which is a lot of Rust developers. We always want to rewrite things in Rust, and there's definitely a bit of a desire to do that sometimes, but we have really benefited a lot from being able to use all these existing things. And it frees us from having to update and maintain all those tools, which is the real secret. So, like, how does CodeGen work? Well, we talked a little teeny bit about Smithy earlier and how we use that to define our models. Our CodeGen will look at those models and turn them into REST. So it will look at Smithy primitives. Smithy has its own way of defining integers and strings and things like that, and turn those into Rust primitives. it will take all those Smithy shapes, which kind of look like Rust structs, and actually convert them into this abstract thing called a symbol, which then gets converted into a Rust struct. And one of the cool things that we do with this is that in Smithy, not all operations are defined with both an input and an output struct. And we're going to look at a model and talk about this in a little bit more detail later. But because of the way that CodeGen works, we can prevent backwards incompatible changes based on people adding new things. And I'll show you exactly what that looks like later. We define these writers, which are basically super-powered string formatters to create files and insert this Rust code into them. We also have things that will create Rust crates for us and manage the dependencies of those crates. We have all these things that will set up serialization and deserialization for all these models so that we can send requests and interpret the responses that come back. It also controls how these service clients get created with all their different operation builders and how their config works. And it also sets up the CodeGen for those specific operations, like how they actually work inside. And then also we have kind of the flip side of this, or rather another layer on top of it, which is AWS specific stuff. So Smithy is actually this generic framework that anyone can use to define any kind of service, not just one that you would see at AWS, but there are other companies that actually use Smithy to define their own services and generate SDKs for those services. For AWS services, that means we need to add a couple of special AWS specific things to our CodeGen. So this is like support for signing our requests. As I talked about earlier, adding user agents to requests, adding AWS specific fields to like service client configs, adding license headers for Amazon to all of our generated files, generating our READMEs for each crate, and then inlining something called inlinables, which is not too descriptive, but I'll explain what that is in a moment as well. So I've been talking about models. We haven't actually looked at one. This is what they look like. You can see that this is the model for that list bucket request that we sent at the very beginning of this talk. And it defines an output, which targets some sort of shape, in this case, the output shape. It also has a couple of Smithy traits, like one for documentation. We actually read that documentation and output that in the crate so that when you go to docsrs, you will see that documentation. And it also says that this is an HTTP operation where we're supposed to get from a specific URI and that a success response is going to be a 200. And so just looking at that is enough information for us to generate this call to list buckets. You'll notice here that it doesn't have an input struct. That's because list buckets doesn't take any input. It just shows you all of your S3 buckets. Now, the thing about that is that in Rust, when you have a function signature with like inputs and outputs, you cannot change that signature without it being a breaking change, right? Like if we added a new parameter to a function and then you update it to that version, that would break your code and stop it from compiling. And we don't want that to happen. We really don't like breaking people. We don't ever want to have to do it. And so in situations like this, it's possible that they might add an input in the model in the future, that the S3 team might modify that model in that way, because for them, that's not considered a breaking change, but in Rust it is. And so what we have to do is we will generate a synthetic symbol. We'll pretend that this has an input that just has nothing in it, just so that we can make sure that when we make these function signatures, that they will never change, even if they add stuff in the future. And there's a couple of more links in here. I link to where all of our Smithy models are. I link to the traits that you can use to customize like a specific model and better explain what it does. Smithy models are defined in either the Smithy language or JSON. In our case, we consume JSON files. If we wanted to do the other way around, we'd have to write an extra thing. But all AWS services are currently output as JSON Smithy files, so that's what we use. So that step that I talked about, just reading the model, that's not exactly quite enough to make a working SDK. So we have all this other stuff too. We have shared types across, all Smithy services that they would need, usually related to HTTP stuff. Other core HTTP things like what an HTTP body is, utilities for setting, modifying headers, things like that. We have our byte stream struct, which is our abstraction over any streaming collection of bytes. So you'll be using that anytime you send a request with a body or receive a request with a body. We have that service client based on Tower that we talked about earlier. We have other utilities abstractions that are kind of, they're not just SDK specific, and they're maybe not even runtime crate specific. They're just used across all of our runtime crates. And we also have the actual code for serialization and deserialization. It's very generic, and that gets put together when we're generating SDKs. And we also have our AWS specific ones. Again, just like with CodeGen, our runtime crates have those two layers, Smithy and AWS. And so this is where we actually define our AWS specific types, where we define how the shared configuration works for all services, where we define how that endpoint resolution occurs, where we define our middlewares and how request signing happens and everything it needs for that. And I glossed over this earlier, but we also have inlinables. So the general thing is that we want to avoid writing Rust within Kotlin as much as possible, because it's not very easy, right, to do all your coding in a string. We want nice like IDE support, and we also want it to be easily testable with existing tools like Cargo and so on. So what we do for that is we have something we call inlinables, which are Rust files that can kind of exist on their own and have tests, but then at CodeGen time, we copied over into that generated crate so that that crate can use them. So that was a lot of stuff, but that is about as deep as it goes. And the core thing to remember is that it's all layers. We have multiple kinds of configuration that all get collected and passed through. We have an operation thing that gets constructed, which gets turned into an HTTP request. And then all that configuration and the request go into some sort of client, which sends the request and receives the response. And we try and write as much of that in Rust as we can. But for stuff where we have to look at the model, it's all code generated. So if that sounds interesting and exciting to you, I would love to see contributions from all of you to the SDK. It's all fully open source. We love getting feature requests from people. We actually prioritize our feature requests based on the number of thumbs up they received on GitHub, because it's very important to our team to make sure that like we're building things that people that want to use AWS need right now. We love PRs. We have a contributor guide that I have a link to in these slides. And we also accept requests for comments, or RFCs, as we call them. And an RFC is a document that's going to propose some sort of change, either to like our code generation or to the SDKs. We write these all the time on the team for large or complex changes, where we want to make sure that they get really good review, because it's not enough for us to build something that works. We want to build the best solution that we can think of that works, one that's really easy and simple to use and understand. Anyone can submit an RFC, and we have a template to help you get started writing one. But if you're afraid to maybe start writing one right away, that's totally okay. If you want to just start by filing an issue with us or starting a GitHub discussion, that's totally cool. Okay, and now it's time for Q&A. So I hope there's at least one question. What do you got for me, Rainer?
Hi, Zelda. Thank you very much. Thank you for this interesting talk. Super well structured. I learned a lot. I have to admit, and I have to apologize if I now ask stupid questions, because I'm not that familiar with AWS. I'm familiar with other cloud platforms, but my day, just like your day, is only 24 hours. I would love to take a look at all these cloud platforms, but I'm not able to. However, okay, I have some questions for you, and I would ask people who take a look at the YouTube at the YouTube stream, please write your questions into the chat. I will relay them to Zelda. But let me kick off with one or two questions. The first one is not directly related to Rust, but I'm curious, and I hope this is not a stupid question. You told us about Smithy and this Smithy language and so on. I know that other cloud vendors, they are primarily generating SDKs from OpenAPI specification, OAS, and Swagger and things like that. Did I understand it correctly that Smithy is somewhat related or somewhat similar to OAS?
I'm not super familiar with OpenAPI. My biggest experience with this sort of thing before Smithy was Swagger.
Uh-huh.
But in concept, I do believe it's very similar. It's just saying that we have some sort of interaction that you can perform with a remote thing. The remote thing will accept this and give you this. And then you read that and generate actual code from it.
Mm-hmm. Mm-hmm. Okay, interesting. I definitely have to take a look at that one. The next question that I have for you is you mentioned at the very beginning that you are using Tokyo, but in general, you want to be independent of the async runtime. We already had talks about trying to write code which is independent of async runtimes. And the general opinion of all our speakers was it is hard to nearly impossible. And therefore, many said, in practice, go with Tokyo. My question is that relevant? Do you see users asking for being independent of the async runtime? What is the reasoning behind staying independent on a certain level?
I would say that the chief reason is just that the runtime that you use today, it may not be the runtime that's supported in the platform you want to support tomorrow.
Okay.
Tokyo is an abstraction over a lot of operating system things, right? But what if you want to run stuff in like a WASM container, or maybe even in the browser, something like that? You would have to potentially use a different async runtime. And so it was really important for us to be able to support that use case because we want people to be able to contact and interact with AWS from wherever they're coming from, not just a computer as we see it, like a normal computer.
Mm-hmm. Yeah, that's super interesting. And I think many people will take a look at that, how you achieve that, because, I guess that many people have that problem. We will see how things go. One question that the audience asks often when we have people here who write more Rust code and have to support it and things like that, I assume I know the answer, but still I want to ask it. Did you had the necessity to write a lot of unsafe code, or is this SDK primarily safe Rust, and didn't you have to to go down to interoperate with existing, I don't know, components, C, C++, whatever?
So most of the stuff that we would have to interact with that would be unsafe would be encompassed within like how we interact with the operating system or something. So like standard library functions or maybe things in Tokyo, and that's kind of a barrier for us. As far as like us actually writing code in unsafe blocks, I think we do it for some of the serialization stuff to achieve speed ups that we couldn't get otherwise. But generally, it's something that we avoid, but it hasn't been particularly hard for us to avoid because there are so many nice frameworks that we can build all this stuff on top of that we actually don't have to worry about a lot of those very, very low level considerations, or at least the low level considerations we have. Async is often not a requirement. When you are doing a lot of web stuff, your code itself is probably not going to be the limiting factor, right? It's going to be sending requests and receiving them over the wire, and that's what's slowest. And so all that stuff is optimized already because we're using things like Tokyo or Hyper. And so we don't have to worry about that aspect that much.
I guess that it would be like that, and that is a very interesting finding. Okay, thank you very much, Zelda. It was a pleasure having you and hearing about how you generate the SDK, how it works with all these fundamental abstractions that you built. It was super interesting, and I'm pretty sure that many people who maybe didn't make it today will take a look at this video. So thank you very much for taking the time again.
Thank you so much for inviting me. This is really fun, and I'm really really
Thank you.
glad.
Enjoy the rest of the day. And I thought I already saw that you joined our Discord server. So if anybody in the audience has additional questions, you can go to our Discord server and contact Zelda there. And Zelda was also so nice to share her screen with us. And I saw that you have links in there. You mentioned them, and I guess in the PDF these links will work. So interesting, people will can grab the slides from there and use them.
Hmm.
Very
Yeah,
well. Thank you.
um, I hope to see you in GitHub. Thanks, everyone.
Hope to see you.
Bye.
Bye. Goodbye. Have a nice evening. So let's say goodbye to Zelda. And that was our first talk. We are nearly in time. We scheduled the second talk, my talk, at 6:20, and now it's 6:26. So I think we can dive right into it. Let me just give me a few moments to set up my environment to bring the right videos on the screen and the right windows on the screen. This is what I wanted to say. This is the first one, and here I need the second one. Let's put that here and put that one here. And with that, I think we are good. I'm going to share my screen now, and I hope you can see it well. Is this the correct screen? Sorry if I need a second. And here it is. Yes, it works perfectly fine. So it's a little bit hard. Please excuse me jiggling around with my slides here and my environment, because doing the moderation and doing the talk at the same time isn't that simple. And I hope it will turn out nicely. So let's dive right into it. The next talk, the next, I don't know, half an hour or however long it will take us. If you have any questions, please send them in the chat. I will try to monitor the chat window here. The next talk will be, I call it constant fun with Rust. You know, my personal background is very much in managed languages like C Sharp, and I did a lot of TypeScript development. I did a lot of Go development, and in the last few years, I focused a lot on Rust. And one of the things that struck me when when I started to work with Rust was the possibilities that you have when working with consts, when working with constants, and especially when working with constant evaluation in constant functions. And this is exactly what I would like to do today together with you. This is a beginner-friendly talk. So if you are rather new to Rust, or if you have already a little bit of Rust knowledge and you would like to deepen your knowledge in this specific topic, that's exactly correct. That's exactly the right talk for you. So let's get started. I have no slides. I will do some live coding, but I have prepared a lot of samples. So you will see me copying some code in, but we will also do some live coding here. So let's get started and get right into the basics. First, it's very simple. So if we have, I don't know, something like this, nearly the answer, we can define consts as you obviously know them from other programming languages. That's very, very obvious. And then we can, I don't know, use these consts and use them in order to build additional consts. Here you see them. Answer, nearly the answer, plus one. And then we can take this one, let me copy in some code and print it on the screen. I mean, that is obvious. I don't have to talk a lot about it. Obviously, this thing here will be evaluated at compile time. This is definitely possible. And you can write a lot of things on the right-hand side of this equal sign, of this assignment of the const. But not everything is allowed in a constant expression. I will share at the end a link to a sample code where I have the samples that I showed here, but with a lot of documentation comments. And there you find a link where you see all the limitations that you have on the right-hand side. But a lot of the things that you would expect here are simply there. Rust is not just capable of doing numeric consts, of course. What you can also do is you can add, for instance, a constant string, and that would look like that. Let me put in that here. That is just a constant string, nothing special, works like a charm. We also can use constant arrays, something like this. Let me put that one here. We can do that, absolutely no problem. Works, oops, sorry, should be here, works like a charm. So this is what you might expect when you come from a different programming language. This is what you already know. Let me surprise you with the first slight small things. Consts in Rust do not need to be declared on the top level. You can declare constants in Rust wherever you want. Wherever you want. You can, for instance, define, let me show you that here. You can define a constant in the middle of the main method. This constant now has a scope. It's scoped to the main method, and we can only use it within this method. Keep that in mind because in a few minutes, we will need that. We will need that because we will find out that scoped constants have very specific properties and capabilities, and I will show you how this works. So this was the basic stuff. Check, first lesson, done. This is the usual const stuff with a little bit extra. Now let's take a look at more interesting samples. First one is I would like to show you that Rust constants don't need to be basic data types. We can, in fact, use more complicated data types. Let me copy in some code here. This is a customer object. This customer object has a string in it and an age in it. And now I would like to define a constant customer. For whatever reason, I might want that, but I'm definitely capable of doing that. I can define here a constant customer, and I can use the struct that I used before. And this definitely works. Let me show you that. I can add a print statement here in order to get rid of the warnings, and now we have a constant customer. So structured data types can definitely work as constants here. That works nice. Let's enhance this sample even further. What if we bring back some constants that we had before? I had this text and the numbers before. Now, could I use another struct I called here named numbers, and when I declare the constant struct named numbers here, can I refer to the constants up here? Yes, I definitely can. So if you have constants, in this case, I have a string and I have an array, you can always refer to these constants and get the address, get the reference to these constants. So with this, we create a named numbers constant, which is a structured data type where I use a constant text as the name and a constant number array here at this member. This works perfectly fine, and I can prove that to you by copying here into the main method. You can try all these things yourself after this talk. I can copy it in, and it works perfectly fine. I can iter over the named numbers. It will get me the correct sum. Trust me, I will not run the program because you will probably guess what the result will be. So this is kind of surprising already. But let me surprise you even more. For that, I'm going to clean up a little bit here. Let's get rid of that one. And let's add a trait. This trait here. I call this trait has numbers, which has a constant numbers and a constant last number with a value inside of a trait. That might be even more surprising for you. Yes, a trait is something like an interface, very similar to what you know from an interface from other programming languages. But in this case, we can have a required constant, an associated constant, a constant associated with the type implementing the trait. We can have that requirement inside of the trait. The second one is very similar. It is also a constant, a requirement on the trait, but we can provide a default value already in the trait. Now let's create a structure. I have numbers, here we are, and implement the has numbers trait for I have numbers. And that works perfectly fine. We can now fulfill the trait by adding an associated constant to our type, I have numbers, and provide the value that we want to have for this constant. We can even override the default value. I've prepared another struct with another interface implemented with another struct, a trait with another struct here for you. Here you see I have the type I have other numbers, and in this case, I'm implementing the existing has numbers trait by overriding the default value which came before directly from this trait here. Here, I'm overriding the default value for the constant inside the associated type, and I can immediately use it as you can see here. And that will give me an array containing 1, 2, 3, 4, 6, because I've overridden the default value of the constant from the trait. So keep that in mind. Traits support consts. The consts that you saw before are free constants. They are not associated to a type. But here we have consts associated to a type. In this case, the type I have other numbers. And those consts can be required by a trait. So maybe you have learned something new about Rust that you don't know from other programming languages. Next chapter, check. Let's go into the next topic. Another thing that is possible with const that you might not expect from when you come from other programming languages. Let's define a very simple structure here. This one will say goodbye, and you maybe can already guess what will say goodbye does. Will say goodbye, as you can see here, is a struct which consists just of a string. It contains a string, and that will be the goodbye message. Now let's implement the drop trait for will say goodbye. The drop trait does nothing more than just printing out the goodbye message that we passed into the will say goodbye structure here. Now we can do something interesting. We can say, hey, let's take this constant here, one, and define it here. Constant goodbye in German. It is of type will say goodbye. And we say will say goodbye auf Wiedersehen, which is the German version of goodbye. And now we can use this constant inside of our main method. In this case, I'm putting it inside of a scope. So what will happen here, we will copy, because consts are by default copied, and we will see that later on, we will copy the will say goodbye constant here. And this constant, the type of the constant, has, in this case, kind of destructor, and it will print auf Wiedersehen on standard out because the variable goes out of scope exactly here. So as you can see, constants can have destructors, and if we use it like that, they will be executed. Okay? So, interesting thing. What you see is that we are reaching a point where we will see that consts in Rust are not just constant values, but they essentially contain code that is executed at compile time. And the next example that I'm going to show you goes into exactly that direction. Let me get rid of that one. As I said, I will share the GitHub link of the whole example at the end of the talk, so don't worry. It will work just fine. Let me see. Yeah, here we are. Let's add some code. This has nothing to do with consts. It is just the thing that we had before, has numbers. Yeah, we saw that code before. I have numbers. Yeah, we saw that code before. Now imagine we would like to write code, a kind of test that verifies that I have numbers implements the has numbers trait. How could we do that? Well, I have a bunch of interesting things for you here. First, we can define constants which don't have a name. They are anonymous. We can use this discard operator, the underscore, to tell Rust that we don't need a name for this constant. You might wonder now, why should we create a constant without a name? If the constant doesn't have a name, we can never ever refer to this constant because it doesn't have a name. That's the whole point of it. It will get even stranger before it makes sense. Let's define the type of this anonymous constant. And in this case, I make it a unit. I make it a unit, so with this, it can just have a single value, the unit. That doesn't make any sense, right? We have an anonymous constant which just can contain a single value, the unit. So let's assign here a value for this constant, and we can do it exactly something like this. Okay. So this will now be code. This is a code block that runs and returns a unit to assign it to this unit to a constant which doesn't have a name. What is the whole point of that? The whole point of that is, let me zoom in a little bit, that this code is running at compile time, not at runtime. And that's the whole magic, which goes into constant function evaluation, which is the next big topic that we are going to talk about. So what we can do is we can add any code here, not really any code. There are some limitations, so you can't write any code at that point. I will show you some limitations later on, but we can in general write nearly any code and execute it at compile time. So here I have prepared some sample code here. And this code will now just use, as you can see here, this struct implements my trait, which uses the has number trait here. And then we will take the I have numbers, and with this code using the phantom data and this helper struct, we can verify that I have number must implement the trait has numbers. The whole point that we have here, if I remove that, we will get an error, obviously, because it doesn't satisfy the requirements of this trait. Yeah. It really, the whole point is that this code is now running at compile time, not running at runtime. And this is what's possible with constant function evaluation here in Rust. Granted, you will probably not write this code very often, code like that, but it was just an introduction for what we can really do with this constant evaluation of functions at compile time. So let's dive right into the next example, which goes into exactly the same direction. Let's copy here this sample code here. This is a regular function. This is a function. Let's remove the const here. This is a regular function generating 5 numbers. It does it rather strangely because we don't use a for loop here. We use a helper variable, a while loop, and just fill an array of 5 numbers with some values and return this array. The point why I do the for loop here is that I can put the keyword const in front of this function, 5 numbers. And by putting the const keyword here, we allow Rust to run this function at compile time when generating the value for a constant. And very important, we can also use it to initialize static members, static variables. So if you have static variables, we can also initialize the static variable with the result of a constant function. So what we can now do is we can define a constant with 5 numbers. Let's put it this here in the main method, and we assign the result of 5 numbers here to exactly that constant. This code does not exist at runtime. It is executed at compile time, and we have this constant, and the value inside of this constant is compiled into our executable and just read from the executable. That's it. So it's really a constant value. And the reason why I didn't use a for loop here is because for loop, unfortunately, are not supported inside of constant evaluated functions. It's not possible. Don't get me wrong, we don't need to use a constant here. We can also use a variable. So constant functions are not limited to applying them at compile time. We can also apply them at runtime. In this case, I have a let, not a const. So I'm using the 5 numbers function at runtime. And now Rust will compile this function, put it into my executable, and I can use it at runtime. So this is what we see here. We can go one step further. Let me show you what we can do if we add a little bit more here. Now, this method, numbers, is a generalization of 5 numbers. What it does, exactly the same as before, but the big difference is that the upper limit of the while loop here is passed in using a const generic. So the takeaway here is that const functions are very powerful. They can be generic and they can even receive const generic attributes. And that gives us a lot of power because with that, we can generate an arbitrary number of numbers in our case. We can declare 10 numbers as an array with size 10. Now, Rust will call this method here. It will derive the constant generic argument directly from the type declaration on the left-hand side. So it will take the value 10 and use it as the parameter n in this constant evaluated function, and it will give us 10 generated values. So if I add, I don't know, 15, the constant generic will change, and therefore we will get 15 values. I think you can guess what's happening here. I can show you that. I can copy that one and maybe go into, for instance, not that one. Need a new browser window. That's the wrong one. This one I prepared. Let's put it here. Let's use the release build. This is the Rust playground, and I'm going to generate the assembler code here. Let's give it a second and I will scroll down. And here you see what I wanted to show you. Here we see 1, 2, 3, 4, 5 constantly evaluated inside the executable. And you can guess what we see down here. This will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This will be the 10 values. This is what I wanted to show you. This is really evaluated at compile time. So this is not a trick. Rust does it at compile time and writes the result of the constantly evaluated methods inside the assembler code, inside of our executable, and we can simply read it from there and consume it from there. This is what we do with this constant evaluations. Okay. I see we have some questions. Let me see. The first one we have to check. The second one, I think I clarified that. And Elvin is asking, are const functions not called in a const context really added to the compiled output? No, they are not. They are just added to the compiled output if I call them at compile time. At runtime, I'm sorry. At runtime. I hope I understood your question correctly. If not, please add the question again or rephrase it a little bit. I hope I understood it. Now, what can we do with this stuff? What can we really do? Where can this be useful? I created a sample which is a little bit longer, and I will copy it in as a whole because it is a lot of code and we only have limited time. I told you that we will spend approximately half an hour on this topic, so I have to copy in a little bit of code. This example is inspired by crates like this one, constr, and you can take a look at it. It's just an example, and but I changed it, I customized it so I can really describe what's going on here. Let's first take a look at this function here. This function is called len, and what it does, it receives a slice of strings. We take these strings and iterate over the strings. Unfortunately, we cannot use an iterator here. Iterators are not supported inside of constant evaluated functions. That's not possible. So we have to use something else. We use slice deconstruction to, in a while loop, get the current value and the rest of the values inside the tail variable. And then we take the length of the current value and assign the remaining here, which is the right-hand side of this while let operation, to the tail. So with this, we have the full slice of strings, then we cut away the first one, second slice, cut away the first one, and we do that and do that and do that until we have no more strings left inside of the slice. And we calculate the total length of all strings passed into the length function. This is what this method does. And because we have written it in that specific way, we can decorate it with the const keyword here at the beginning in order to be able to run this method at compile time. Now let's scroll down a little bit, and maybe you have already guessed what I'm going to do next. I'm trying to build a concat function that accepts a slice of strings and then concatenates all these strings, but doing that at compile time and not at runtime. Let's take a look at this example. It takes the various strings here as an input parameter and allocates a buffer of adequate size. We simply take the total length. We get that again through a const generic parameter. You see it exactly here. And then we have to write again a little bit awkward code because we are not allowed to use for loops. Yeah, but we apply the same tricks as before. We're also not allowed to use iterators, so we will do this this slice deconstruction again, this trick that we had before in the len function. We allocate the appropriate buffer. We had it before, so we can simply copy all the strings into the allocated buffer, as you can see it here. Again, no for loop, so please excuse this code. It is necessary in order to be able to make this method const. And at the end, we simply return a helper struct which contains the concatenated version of all the strings that we passed in here. This is what we do in the concat method. So let's try to apply that. Let me zoom. No, I don't think I have to zoom. Let's put it that way so I can draw a little bit. Please take a look at this line here. Here we are declaring a slice of constant strings which says hello world. Here, we are using a constant where we call the constantly evaluated function len, so we are calculating the total length of all provided strings in line 62 inside of another constant. Then we take here the concat buffer and we use the constantly evaluated method concat that you have seen a second ago in order to get a buffer, which is nothing else than, again, an array of U8 of bytes which represent the string. And last but not least, we use a method from the standard library from UTF-8 unchecked to turn it into a string, and we can print it on the screen. So at the end of the day, we were able to take all these constant strings and concatenate them to receive a single string at the end. And all the magic is done at compile time and not at runtime. Now, if we hover over here, over this from UTF-8 unchecked, it's obviously very important that this method from the Rust core library also has the const attribute here. It is also a const function, because otherwise we weren't able to use this function here in a const context. It wouldn't be possible. But with this, that is perfectly fine. And again, don't get me wrong here. We can do exactly the same, but this time at runtime. So here you see again our strings. We already have the len calculated. We use the concat method, which works perfectly fine at runtime too. We use the from UTF-8 unchecked, perfectly fine at runtime, works like a charm. But the const in front of the function allows us to use the function in a const context. Okay? So let's try that with a little bit of macro magic. My good friend Elvin convinced me that macros are super useful. So I tried to build a macro here that makes applying this len and concat function in a little bit easier. Elvin did a great talk about macros last time. So I tried to apply this knowledge directly here in this talk. So as you can see, this is exactly what we have done down here, but just written in a macro. This macro takes some strings as parameters, as you can see it here, and we are doing exactly what we did down here. But that makes it way more convenient. We can just say my concat, which is the macro, give it the first string if we want. Here, this is a const string. Give it here a literal, and give it here another const string. Some of you might say, hey, we don't need that because there is already a concat macro built into Rust. Yes, that's possible, but this concat macro that's built into Rust does not accept here constants. We have to, I don't know, do something like that and have to add the cat, and we have to add the, I don't know, mouse here. Yeah, it works perfectly fine. This works. This is built into Rust. We don't need a manual macro here, but I wanted to build, just for demo purposes, a version of a concat macro which is capable of referring to another constant, just for demo purposes. In fact, there are a lot of crates out there that contain lots and lots of helper functions capable of doing string concatenation, capable of combining strings with values, with integer values, and so on and so on. Just use your favorite search engine to look for crates that contain const functions that you can use in a const or static context. But I hope this example was somewhat useful for you to understand what we can achieve if we don't just write trivial code as we had it before, but a little bit more extra code, a little bit more advanced code that we can execute at compile time. Okay, now the latest and greatest versions of Rust added a bunch of extra things with which I would like to close my talk today. Okay. So, the first thing that I would like to show you is the possibility to add trait bounds to generic constant functions. Let me copy in a little bit of code here. This one. Here we are. This is a little bit of code. Here we have the customer here, and we have a constant customer, nothing special here, works perfectly fine. Now we can, as I showed you before, define constants not just on top level, but we can also define these constants inside of the main method. And here I'm doing something a little bit different. I'm creating an array of two customers. We have the customer John and we have the customer Jane. And now I would like to write a constant function that takes the nth element from an array and copies it out here. And this is how you can do it. This is the constant function. And with this constant function, we can copy out the nth customer. Let's analyze this function. The constant function, the implementation is trivial. That's not the point. It gets an items array here with a constant generic parameter, and it gets the required index as the second parameter. But the important thing that you see here is that one. This is new. This is brand new. In fact, it became possible, stable, in Rust 161. 1.61 is the version of Rust that makes it possible to specify generic parameters for constant functions. Sorry, trait bounds on generic parameters for constant functions. This is new, and this is now possible. So if you need that, take a look at it. It works like a charm. The second example, which is new, regards to impl and dyn traits, to trait objects. So let me get rid of that example here. Here we are. Let me get rid of that example, exactly. And then I can bring in a little bit of code. I'm going to show you what we can do with that. Now, this is a kind of classical example when it goes to polymorphism. Here we have a trait animal, which has a method make sound, which just returns the sound that each animal makes. We have a cat and we have a dog. The cat says meow and the dog says woof. Pretty clear. Nothing to do with constant evaluation or something like this. That's perfectly fine. Now let's add here a helper method, and this time it's a constant method, and this is again brand new for Rust 161. So if I add that one, you will see that this method generates my favorite animal, which happens to be a cat. We have two cats. And the new thing is the support for impl here. We can return an impl trait from a constant function. And that works perfectly fine. Let me show you how that looks like. If we copy in the code into the main method, here you can see that I'm calling this favorite animal constant function here. And then we can assign it, for instance, here to a trait object and then call it this make sounds directly here. But this favorite animal returns an impl trait, and that one is new. Just like returning an impl, we can also do dynamic dispatching. Do dynamic dispatching with something like that. In this case, I am implementing a method which is called animal by sound. I specify a Boolean value saying whether the animal has to be able to purr. If this is true, this has to be a cat. Otherwise, this has to be a dog. This is just for demo purposes. But the point is, the return value here, the return type, is a trait object. So we are returning a din trait object from this function. And that, again, is a brand new feature in the Rust version 161. And again, let me demonstrate that. It works like a charm. If we put it here, you see animal by sound, this returns the din trait object. We can assign it, and calling it works perfectly fine. Okay, so these were two new things that came with Rust 161. And I would like to close with one final demo that looks a little bit into the future. Let me show you this example. Sorry, I have to switch between my Visual Studio codes. Here we are. Let me show you something here. And in this case, I'm doing that one. You all might be familiar with tricks for how to create a static mutex. I just opened up a Stack Overflow post, which is very, very highly appreciated by many people, and it shows how to use a new mutex, a static mutex. You see tricks like lazy static, using one cell, using many other possibilities, just tricks that you need in order to create a static variable holding a new mutex. And this is now no longer necessary. Let me bring in the type here. And as you can see now, with the nightly version of Rust, which might come with Rust 163, the new function and various other functions in the area of sync types are now const. So you can see it here. Mutex new it can be called in a constant evaluated context, and we can do that here. Let's put it that way, const. This is what I wanted to show you here. This is the const thing, and then we can also use it. Let me show it to you. This is my array, and here we are. This is the code. There it is. This is how we can use it. Now here we have the array. What did I do wrong here? Yeah, this is what I wanted to show you. Here we have a static value. I need to, of course, I told you, sorry, I'm not that good in typing and talking at the same time. Of course, I cannot change that to a const because it isn't a const. It should be a static. That's the whole point here. But I told you that constantly evaluated functions can be called not only in a const context, but especially in a static context. So here we use the mutex new, and it's possible because it is now a const. If we copy this one into our Rust playground, where is the Rust playground? I think it is here. Here it is. And we try to run this thing, it will probably not work. Exactly. You see that here we have the problem in the stable version that mutex new is not a constant function. We cannot call it here in a static constant, in a static context. But what I can do, I can change that one to the nightly channel and run it again, and it will hopefully work just fine. Yeah, it worked just fine. This is new, this is coming, and a lot of additional methods are now const methods, and that make it much easier to consume them in a static context. I can't say context today, in a static context, as I showed you in this sample. So my goal for today's talk, let me get rid of my screen here. My goal of today's talk was a quick introduction what Rust is capable of doing. I promised you that I would like to share my samples with you, and I will do that immediately. Give me a second. I will look it up here in my GitHub repository, and here it is. I will now paste in the link to the entire sample, including all the comments inside of the code, and I can also share another file with you, which I will paste on the Discord channel. So if you are on the Discord channel, feel free to grab the following links. I go to my Discord server here, and here it is. And I will show you that in a second. Give me a second. Okay, sent it. What I did for those of you who would like to take a closer look at these samples that I showed you in my GitHub, in the Discord server, I have created a link to every single sample that I showed you today. So I want you to be able to try all these code snippets. You can click on these links, and these links will bring you directly into the Rust playground in order to try with it, to play with it, to see whether I did something wrong, or to extend my samples, or whatever you want to do. So this is what I wanted to share with you, because I think if this is a beginner-friendly talk, it is important for you to be able to try to play around with these examples. And that is essentially all that I have for you today. I promised you that it will take approximately half a minute to walk you through some new things that Rust is capable of doing in const contexts. So let me see if we have some additional questions here. Okay, I see that my good friend Elvin asked some questions. Let me see if I can answer some of them. Okay, the first one we already have. Okay, this question here, we can discuss them later on, but you can also take a look at my samples here. And yeah, Elvin, you are perfectly right. In some areas, my code is a little bit over-specified. So what I did, I specified at some places, I specified the length of the array and so on, just for the reason of clarity. You are definitely right, and thank you for pointing that out, that we can remove the length in some areas because we simply don't need it. Rust can infer it automatically. Okay, thank you, Harold. Thank you very much. I'm glad that you liked it. And again, I will put the links to all the samples on Discord right after my talk. I just saw that Discord complained that the whole text was a little bit too long, so I have to put them together, shorten them a little bit, but in, I don't know, 10 minutes or so, you can find all the links to all the samples on my Discord server. And that is what I have for you today. Thank you very much for listening. Thank you for staying with us on this beautiful evening. Enjoy the rest of the evening. And I have a very special announcement. In July, I think it is on the 21st of July, we will have our next Rust meetup, and that will be our birthday meetup. We already have fixed a very special guest, and we are looking forward to this guest. We will announce it on Twitter, on Rust Linz AT, and on our meetup page. I hope you will be with us. And for today, I want to say thank you. Thank you for joining us. Thank you for listening. And make sure to watch the recordings on YouTube. Thank you. Goodbye. Have a nice evening.